It's February 5th, 2026. And, if you've been following the headlines in biotech, there's this mental image we all have of AI right now.
The biological crystal ball.
Exactly. That utopian idea. You feed a genetic sequence into a computer and poof, out comes this perfect 3D model of a protein or a drug. We've been told the problem is solved.
Solved is a very heavy word in science. We've definitely been told it's predictable. But there's a huge difference between predicting something because you understand the physics.
And predicting it because you've just memorized the answer key.
Precisely. And that's really the distinction that matters.
And that's exactly why we're here today. We're looking at two documents that are basically crashing that problem-solved party.
A big day for it.
First, we have this massive new audit in Nature Communications. It's called FoldBench, and it feels like it's accusing all the top AI models of, well, cheating on their exams.
And then, just hours ago, a breaking technical report from the Proteinics team at ByteDance Seed.
Right. And they're claiming to have fixed what FoldBench says is unfixable. It's a lot to unpack.
It's chaotic. So what we're trying to do in this deep dive is, reconcile these two things. On one hand, you have FoldBench saying our best models, AlphaFold 3, Boltz 1, Chai 1, are just hallucinating when it really counts.
And on the other, Proteinics is saying, no, we found a way to brute force our way to intelligence.
Using open source tools, which is key.
So the mission today is to figure out, do these AIs actually get it? Do they understand the laws of biology? Or are they just incredible at matching patterns they've seen before?
Because if you're a drug hunter, that distinction is everything. It's the difference between $1 billion drug and $1 billion failure.
Exactly.
Yeah.
And to get there, we have to start with this idea of homology.
Yes. Let's start with FoldBench.
Okay, the FoldBench audit. This isn't just another leaderboard. Reading it, it feels less like a paper and more like a forensic investigation. What's the core accusation about data leakage?
The core accusation is that all the amazing success rates we see are inflated because the tests are too easy.
How so?
Well, when you train a model like AlphaFold, you show it the protein data bank. Basically, our entire library of known protein structures. But the thing is, biology recycles everything.
Evolution is lazy. It reuses the same parts over and over.
It's efficient. So if an AI sees a specific protein shape during training, and then you test it on something that's, say, 90% identical.
It's not really solving the problem from scratch. It's just remembering the answer from last week's homework.
It is rote memorization, exactly. It's like a math student who memorized that 2 + 2 is 4, but has no idea what plus actually means. They get an A+ on the test, but they can't do math.
So FoldBench says to really test them, you need what they call low homology targets.
Yes, and they're ruthless about it. They took structures from early 2023 to late 2024 stuff the AIs hadn't been trained on and threw out anything with more than 40% sequence similarity to the training data.
40%, that's a low bar. That means the proteins they're being tested on are practically alien to them.
Alien is the perfect word. They call them unseen targets. And when you do that, when you take away that safety blanket of familiar data, the performance graphs, they start to look pretty rocky. The models start to sweat.
The part of that report that really jumped out at me, and I think this is the key takeaway for anyone in pharma, is this unseen ligand trap.
Yes. Because we're not just folding proteins for fun, right? We're trying to stick drugs into them.
You want them to do something.
Right. A ligand is just the drug molecule. And FoldBench found this fascinating split. If you give, say, AlphaFold 3 a protein it's never seen, but you ask it to bind a drug molecule it has seen before.
Like aspirin. Or something common.
Exactly, a common chemical piece. If the ligand is familiar, the AI does okay. AlphaFold 3 hits around a 69% success rate on these unseen proteins.
Okay, almost 70%. That's still pretty good.
Right.
That's a useful tool.
It is, but, and here's the trap, the second you introduce an unseen ligand, a totally new drug molecule, a chemical shape the AI has never memorized, the accuracy just falls off a cliff.
Which is the entire point of drug discovery.
Yeah.
You're trying to invent new molecules. Pfizer isn't looking for a drug that already exists.
And that's where the illusion of understanding just shatters. If the AI actually understood the physics of binding, electrostatics, steric hindrance. It shouldn't matter if the molecule is new. Physics is physics.
A carbon atom is a carbon atom.
Right. The fact that it fails suggests it's using chemical memory. It's thinking, oh, I've seen that shape. It usually goes here. Not, these atoms will fit together because of their energy states.
So it's not simulation. It's just very, very sophisticated pattern matching.
It's high-dimensional pattern matching, masquerading as physics, and when the pattern is new, the mask slips.
That becomes so obvious when you look at the case studies. We have to talk about PDB ID8FNY, the kinase enzyme story.
Ah, yes. The case of the nervous AI. This is a perfect example of what we call bias in the system.
Okay, set the scene. A kinase enzyme, and we're trying to bind a molecule, ADP, to it.
Correct. Now, 99% of the time in all the textbooks, ADP binds to the active site. It's the front door. But in this specific structure, 8FNY, the ADP actually binds to an allosteric site.
A hidden pocket, a back door.
A back door. And finding those back doors is the holy grail of drug design. It gives you much more subtle control over the enzyme.
So they fed this to the models. What happened?
Well, Boltz 1, Chai 1, they all failed. They just jammed the ADP into the front door, the active site, because that's what they've always seen. They just went with the statistical average.
But AlphaFold 3 did something different.
This is the really heartbreaking part. AlphaFold 3 actually found the back door. In its raw generation phase, when it was just brainstorming ideas, it produced the correct structure.
So it had the right answer.
It had the right answer in its hand, but then comes the ranking phase, where it assigns a confidence score. And it looked at the correct answer, the back door, and gave it a low score. It basically said, this looks weird, ADP doesn't go here, I must be wrong.
Wow. It second-guessed itself because of peer pressure from its own training data.
That's a great way to put it. It reveals this fundamental flaw. The models bet on the most likely outcome. But innovation, especially in disease, often happens in the unlikely outcome, the weird exception.
Okay, then there was the other failure, the shapeshifter, PDB-ATPA. This one felt less like bias and more like a total blind spot.
The domain swap dimer. Yeah, this is a really tough one.
So to visualize this for everyone listening, instead of two proteins just sitting next to each other, they actually open up and swap parts. It's like they're shaking hands, but their arms are physically entangled.
It's a topological knot. So the Foldbench team gave this to the open source models, and they all just predicted two separate lonely proteins.
They didn't see the handshake.
They didn't even know a handshake was possible. Only AlphaFold 3 managed to get that complex, entangled shape right. It just shows that the other models really struggle with massive shape changes.
And that brings us to the final boss, antibodies.
Everyone wants to design antibody drugs. It's a huge market. But structurally, they are a nightmare.
The report says AlphaFold 3 has a success rate of just 47.9% on antibody-antigen interactions. That's a coin flip.
It is not good. And the others were seeing failure rates over 60%. And it all comes down to this one tiny hypervariable loop called the CDRH3 loop.
I saw the pictures. It looks like a little straight piece of spaghetti sticking out of the protein.
That piece of spaghetti is everything. It's the finger that pulls the trigger. In one example, they showed two predictions from the AI. In one, the loop was placed correctly within 0.17 angstroms.
Which is atomic precision.
Yes, and that prediction worked perfectly. But in another guess, the loop was off by 3.07 angstroms.
3 angstroms sounds tiny.
In our world, 3 angstroms is the Grand Canyon. If you're off by that much, the atoms don't touch. The drug just floats away, completely fails.
So the AI is inconsistent. You can hit the bullseye, but it also throws darts into the wall, and it doesn't always know which is which.
Exactly. And until yesterday, that was pretty much the state of play. AlphaFold 3 was the king of a flawed kingdom, and open source was struggling to keep up.
Which brings us to today, February 5th, 2026, and the Protenix paper.
The timing is just incredible, right? Just as Foldbench is laying bare all the problems, Protenix drops Protenix V1, and they are coming out swinging.
They're not just saying they're good, they're saying they're the first fully open source model to effectively tie with AlphaFold 3 on these hard targets.
And that open source part is huge, because AlphaFold 3 is proprietary. You have to use Google Server. You can't just download it and run it on your own secure systems. Protenix is giving that power back to everyone.
But how? How did they catch up? Was it just a bigger model? More data?
No, and this is the most important technical shift for everyone to understand. It's not about training. It's something called inference-time scaling.
Inference-time scaling. Okay, break that down for me.
Think of it like this. Most models work on reflex. You show them a problem, they give you one quick answer. That's system one thinking. But what if you told the model, don't give me your first guess. Take your time. Generate 1,000 different possibilities. Then pick the best one.
So it's the difference between a gut reaction and a long, deliberate brainstorming session.
Exactly. Protenix V1 showed that if you increase the sampling budget, if you let it generate more and more guesses, the accuracy just keeps going up in this nice straight line, a log linear improvement.
Wait, does that mean the model isn't necessarily smarter? It's just working harder?
It's exploring the space of possible answers more thoroughly. Remember the kinase where AlphaFold 3 found the right answer but then threw it away?
Right.
If you force it to generate enough samples and your ranking is good, the correct answer eventually floats to the top. Protenix showed that by just scaling up this thinking time, they could match AlphaFold 3 on protein interactions.
They actually took a shot at the fold bench scoring in their report too, didn't they?
A little bit. They pointed out that some of the comparisons weren't quite apples to apples, so they released their own corrected fold bench. And on that level playing field, with inference time scaling cranked up, Protenix V1 hit a 72.7% success rate on protein interfaces.
Which, as you said, effectively ties AlphaFold 3.
It does. It basically democratizes high-end protein folding. If you're a startup, you can now run this in-house and get the same quality as the big guys. That's a massive shift.
But, there's always a but, they caught up on proteins. But what about the unseen ligand problem, or the really hard stuff?
And this is where we hit the wall again. The final frontier, nucleic acids, RNA, and DNA.
We touched on this, but how bad are the numbers, really?
They're abysmal. If a good protein score is like 0.9 out of 1, the scores for RNA and DNA are down in the 0.2 to 0.6 range.
That's not a prediction. That's a random guess.
It's a random scribble. The Fold Bench report showed an example of a large RNA aptamer, PDB7ZJ4. The AI gets the little local bits right, the little hairpins, but the overall 3D shape, the global structure,
a total mess.
The error metric, the RMSD, was 20 angstroms.
Whoa. Yeah, we were just saying 3 angstroms was the Grand Canyon. 20 is.
It's a different solar system. It looks like a tangled ball of yarn. It is completely useless for any kind of drug design.
So why is RNA so much harder? Is it just floppier?
It is floppier. That's part of it. But the main problem is just data starvation.
We don't have enough examples for it to learn from.
Not even close. Nucleic acids are only about 8% of the protein data bank. The AI has seen millions of protein shapes, but only a tiny fraction of complex RNA shapes. It just hasn't seen enough to learn the rules.
And there are specific structures it just can't handle it all right. You mentioned a G-quadruplex.
Yes. It's a specific, really dense knot of RNA that forms in sequences with a lot of guanine. Fold Bench looked at one from the West Nile virus.
And the models.
They all choked. AlphaFold, Protenix, all of them. They just tried to unwind it into a simple ladder, but it's supposed to be a dense knot. They fundamentally misunderstand the physics.
And this is so critical. RNA therapeutics are supposed to be the next big thing. But if our AI is hallucinating the target's shape by 20 angstroms...
We're flying completely blind.
Okay, let's zoom out. Here we are, early 2026. AlphaFold 3 is still the king, but now it has an open source twin in Protenix V1. What's the synthesis here? Where do we actually stand?
The synthesis is that we're hitting the absolute limits of a memorization-based approach. We have built incredible tools that can remix things they've already seen. Protenix proves that if you just throw enough computing power at the problem, that inference scaling, you can brute force your way to accuracy for things that look familiar.
But we haven't made the leap to understanding from first principles.
No. The unseen ligand problem and the RNA disaster prove that. The AI doesn't know why molecules bind, just that they usually do. To get to that next level, we can't just keep generating more samples. We might need to actually teach the AI chemistry, not just history.
It's fascinating that the solution right now is just think harder or guess more. It feels like trying to win the lottery by buying 1,000 tickets instead of one.
And it works, to an extent. That's the power of modern computing. But it raises a really provocative question for everyone listening.
What that?
If these models get better just by generating more samples, by guessing and checking 1,000 times, are we reaching a limit of artificial intelligence or just a limit of our computers? At what point does guessing 1,000 times become indistinguishable from actually understanding?
And if the result is a cure for a disease, maybe you don't care if the AI guessed or understood.
Perhaps. But until it works on the truly unseen stuff, the weird RNA knots and the brand new drugs, I would definitely keep the wet lab running. We're not ready to retire the test tubes just yet.
A sobering but exciting place to be. That's all for this deep dive into the molecular matrix. Thanks for unpacking all this with us.
Always a pleasure.
We'll see you in the next one.